here is our picture. So you'll see we've got some sort of ducting here. It's saying it's the ducting of head of chiller coils in an AC system. Notice it's steady state data that's given on the picture. We're going to have outside air that is mixed in with return air. So here's the outside air coming in. Here's your properties. You got your temperature, your velocity. Notice it's in feet per minute. You've also got your volumetric flow rate. The return air is at 75 degrees, gives you the diameter of this opening, and then it gives you the velocity there. Pressure is going to be 1 atmosphere throughout this system. And then at exit point 3 here, we're going to have mixed air. Velocity is going to be 500 feet per minute, and we want to find T3 and D3. Now it also tells us that stray heat transfer is negligible, as is kinetic and potential energy. We're going to model this air as an ideal gas. Gives you your CP value. So we want to find this temperature at point 3 and the diameter of the exit. R is given to you, and also mass flow rate for the air. The outside section is given as 144.29. All right. So now that we've got that, let's go ahead and get started. First, what we need to do is we need to look at our mass flow rates. And the reason why we're going to do that is because we need to find a temperature. So we're going to have some way of getting a temperature. The equation we're going to end up using will be the energy balance to get that, and we need mass flow rate for that. So let's go ahead and get started on mass flows. Now we already have M1 dot. I kind of gave you that to shorten the problem. That's why it wasn't on the picture. So M1 dot, if you go through and use the volumetric flow rate and everything, solve, you'll get 144.29 pounds per minute. Now let's find M2 dot. So remember, that's going to be your volumetric flow rate at point 2 divided by the specific volume at that point. So now if we have that, notice it is an ideal gas. So with that, what we could do is we could say that this is equivalent to the A times V2, and then in the denominator here, since pressure equals rho RT, and we know that 1 over rho is V, then we could write that V is RT over P. Alright, so you just kind of reorganize this to solve for V. Now let's use this down here. And that'll keep us from having to look values up in the table and everything. So now we've got this like that. Alright, so now we're going to have to find the area at point 2, which we can find because we were given diameter. We need velocity, which we have that. We've also got temperature, and we've got pressure, because pressure is 1 atmosphere for all the whole entire system. So let's go ahead and fill this in. The area is going to be pi r squared. We're given diameter, so we need to divide that by 2. So we're going to have pi times 2, essentially 4 divided by 2. Square that, and then we're going to take that, that's our area, multiply it by the velocity, which was 400 feet per minute. And now in the denominator, we've got RT over P. Your R is 53.33. That's foot-pound force per pound degree Rankine. And we also need temperature. So our temperature at this point, we're given 75 degrees Celsius, or not Celsius, Fahrenheit. We can't use Fahrenheit in here. We need to have the absolute temperature scale. Notice we got degree Rankine here. You need to convert 75 over 2 degrees Rankine. If you do that, you get 535 degrees Rankine. Then we're going to divide by pressure. All right, so our pressure is 1 atmosphere. We don't want to use atmosphere in here. Notice we don't have atmospheres anywhere else in here. That is equivalent to 14.696 psi. Now we don't have inches anywhere, so we got to do that conversion. So let's multiply by 144 inches squared per square foot. And now, finally, all of the units work out. Degrees Rankine will cancel, inches squared cancels, your feet squared cancel. Everything's going to end up canceling out. All right, and what you're going to be left with will be the mass flow rate units, which will be pounds per minute. So let's put M2 dot equals 372.82. That's pounds per minute. All right, so now you have that. Those are gone too. Okay, so that is our mass flow rate at point 2. This is 372.82. Now, let's see what else we need to do here. Actually, we weren't asked to solve this. I just boxed it, just to box it, I guess. Now let's go to point A. Now on point A, we want the mixed air temperature. All right, so that's the temperature coming out at point 3. Let's go ahead and do our energy balance equation. So we're going to have 0 equals Q dot minus W dot. And the control volume is going to be this entire thing. So we'll have all the inlets and exits. We'll have M1 dot times H1 plus M2 dot H2 minus, because this is an outlet, M3 dot times H3. Now this term goes away because we're ignoring stray heat transfer. W dot doesn't say anything about power being required or power being generated, so let's get rid of that. Then we're just left with these 3 terms. All right. So now that we have that, notice we've got these 3 M dots. Now we know M2 dot because we just did that, and then we also know M1 dot because that was given. We don't know M3 dot yet, but we do know this is steady state. So if it's steady state, what does that mean? It means the mass flow rates of the inlets have to equal the mass flow rates of the outlets. So we can write that M3 dot is M1 dot plus M2 dot. And again, that's from steady state. All right, so we got that, and now we can take this, plug it in here. So I'll have 0 equals M1 dot times H1 plus M2 dot H2 minus M1 dot plus M2 dot times H3. Now we got the 2 M dot terms. Let's go ahead and group the terms up based on M dot. So I'll have 0 equals M1 dot times H1 minus H3 plus M2 dot times H2 minus H3. Now we can plug in our values. Notice before we do that though, we're given this CP value. We've got an ideal gas with a CP value given. Remember, you can find your enthalpy values using CP times temperature. So that's what we're going to do here instead of going into the tables. All right, so let's go ahead and fill this in. We're going to have 0 equals 144.29 pounds per minute times that CP value, which is 0.24. That's BTU per pound degree Rankine. And then multiply, let's make this a bracket, multiply that by the change in the temperature. So we need T1, and then we're going to need T3, which we don't know T3. We're looking for that. T1 is 90 degrees Fahrenheit. You need to convert that over to Rankine. That's going to be 550. Subtract T3, and then put this term in here. So we're going to have plus 372.82, that's pounds per minute. And now, again, you'll have the CP value, so the 0.24. And now you need T2 minus T3. Okay, so T2 is the 75 degrees, and that's 535 degree Rankine, and then T3, we don't know what that is yet. So let's just leave it as T3. Okay, so now you got that. Now that you've got all this, you've got one unknown. So you've got T3, it's in both these places, so you'd have to do some algebra here, get it all together, and then you can solve for T3. And that's going to give you 539 degrees Rankine. All right. So that's what you'll end up getting. And in Fahrenheit, because it wants it in Fahrenheit, that's 79.2 degrees Fahrenheit. So you'll have that. Last thing we need to do is find the diameter of the duct at point 3, at that exit point. Now our equation with area is going to be the mass flow equation. And remember that that is rho AV, which is also AV over specific volume. And we also know that at point 3, M3 dot equals M1 plus M2 dot. So we have that relationship there that we can use. All right, so now with that, if you put M1 dot and M2 dot together, you're going to get 517.11, that's pounds per minute. So I know that this has to equal that. And we don't know specific volume, so let's use the thing we did up here with the ideal gas. Let's put RT over P. And these are all for 0.3. So now you get that. Now all you have to do is plug in your values. Let me get another sheet here. So we'll have 517.11. And then that's going to be the area. We're going to have pi r cubed, or not r cubed, r3 squared. And then we multiply that by the velocity. We were given the velocity as 500 feet per minute. So that'll be useful. And then you're going to have to put it over RT3 over P3. All right, so R was given to you. That was 53.33. So let's write that out. There's R. T3 we just found. Remember to use the degrees Rankine value. And then you need to put that over P3, which is 1 atmosphere, but we can't use atmosphere in here, so you got to have the 14.696 pound-force per square inch, and then convert over from inches squared to feet squared. Now, if you go through and then do all the units and everything, you will see that they all work out to where when you solve for R3, you get feet. So what you're going to do is solve for this R3 value, which is your radius. You'll get 2.11 feet. We want diameter, so just take this, multiply by 2. And then you'll get your diameter is 4.22 feet. Okay, so that is what it will look like.